Hello, welcome to 8.4 normal approximation of the binomial distribution. Please look at the images in front of you. As you'll see, one is the binomial distribution, the other is a normal curve, standard normal distribution. Alright, let's get started. So just remember, the discrete binomial probability distribution gives x successes in n trials using the formula as such. So we can use an example of this is if we're rolling a 6-sided die 18 times, what is the probability of getting 1 or 2 exactly 8 times out of those rolls? So we can use that formula to calculate it. We can use a probability distribution to see all the different probabilities of getting 1 or 2 out of the 18 rolls. You've seen that, so if you want to, you can go back and review that if you want to. Right, so the thing to recall, the standard normal probability distribution can be used to approximate discrete probability distributions given that the data set is large enough, is symmetrical, and the mean and standard deviation are known. Well, as you can see from the very first slide, the binomial probability distribution is symmetrical, giving it that bell curve kind of look. And stats theory states that we can continuous normal distribution to approximate the discrete probability binomial distribution as long as n is greater than np is greater than 5 and nq is greater than 5. So why do we need these? Well, they both demonstrate that a set is large enough. It also gives us that the mean is n times p, and standard deviation is the square root of n times p times q. Okay, so from our previous exercises, we saw that rolling our die 18 times and we're looking for 1 or 2, exactly 8 times. Well, we can check and see n and p are n times p and n times q are greater than 5. So we calculate n is 18 and p is 1/3, so I switch them, but it's commutative, so it's alright. So that's equal to 6, and n times q is 2/3, and n again is 18, so that's 12. So they're both greater than 5, so we can use the normal approximation. But we have choice. If we're using the graphing calculators, we can use our norm CDF, which we've used in the past. We can also use what they call a binomial CDF, or a binomial approximation cumulative distributive function, as long as we know NP, the low value, and the high value of an interval. Okay? Note that the high value cannot exceed n. Makes sense if you think about it for a second. As well, we can also use the z-score, which we've also been visiting for the last few days. So let's use these three methods and compare them to the binomial probability distribution, see which one is actually more accurate. It's always a good problem, good question to ask. So here we are. There we go. So here we have the binomial probability distribution in discrete chapter 7. Okay, so that comes out to be 11.5%. So the probability of getting a 1 or 2 8 times out of 18 rolls is 11.5%. Yeah, sounds good. Okay, can do our normal approximations. So norm CDF. So we're going to use, remember, adjusted from the continuous to the discrete, so we have to use 7.5 and 8.5. NP is our mean, which is 6, and if we do a quick calculation, we can find out that square root of n times p times q is 2, which is our standard deviation. Plug all those numbers in, calculator gives us 0.12, 12. 12%, yeah, not too bad, it's close. 11.5, 12, you can see there's some rounding going on, so that's okay. Let's try our binomial CDF. Again, we have n is 18, p is 1/3. Again, we're doing our adjustment, so we have 7.5 and 8.5, and wow, look at that. The numbers are almost exactly the same, which they are exactly the same. That's kind of cool. And then, of course, we can use our z-scores, and it gives us some weird number like 15%. It's a little bit off. Not sure what happened there, but, things happen. Alright, we also have to subtract a few values less than this because this is giving us the cumulative up to that point, rather than the interval. So my apologies. Probably if we did that calculation twice and then subtracted them like we did with the other ones, we'd probably get a much closer, more reasonable answer. But alas, we did not do that. So just note to ourselves. So we can see from the last question that using the binom CDF function in the calculator will give us the most, apologize for that, crazy computers, will give us the most accurate approach and most accurate answer rather than using binomial distribution, which can be used sometimes, but occasionally using the normal CDF, binom CDF will give us answer a little bit faster. Let's put it that way. So there are some questions to try, and we'll try some more on Monday. Hope to see you there. Have a good weekend.